In this video, we are going to talk about one of the very important concept of derivatives. So we're going to look at the situation. We have a function to a power of a function like fx to a gx. So when you have function of a function, there are four things can happen. So for example, first, the both of them can be constant. So the first case is both are constants. If both constants, so this situation is like 2 to the cube. So 2 to the cube is a constant and we know the derivative. So the derivative is 0. And the second one, the gx function is a constant. So the gx is constant. Gx is a constant. So I'm going to say c. So a situation is like this. So you can say x to the squared. So this is like a second function. The gx is constant. So the third one, the fx function can be constant. So we have the situation where fx is a constant. So this is like 2 to the x. And then the last one is both are not constant. Both are functions, non-constant functions. So both of them are non-constant. So for example, a situation is like x to the x. So the goal of this video is to understand how to take the derivative of in these cases. And you will see that there are 4 different techniques to follow. So let's go one by one. Let's start with the first one. So this is the easy one. So we have, let's say, y equal fx to gx, and then both are constant. If the both are constant, so you get a constant. This is a c, let's say call it c, and then we know that the derivative of a constant is 0. So that means the derivative of the y function is simply 0. So that's the first case. You get a 0 derivative. So as an example, let's say you're going to find the derivative of, pi to the e. We know the pi to the e is a constant, so that means the derivative is 0. So that's the first case. So let's look at the second one. So the second one, gx is a constant, but fx is not. So the situation is like this. So in this case, you're gonna see your function is like fx to a constant. So that's like a situation. Fx to a constant power. N is a constant. So n is a constant, what we can do, we can use the power rule and the chain rule. So we can use the power rule and the chain rule. So use power rule and the chain rule. So that means you can write a formula for this one. So few cases is like this. So we have d by dx, x to the n. So that's the most common one. And we know that just a power rule. So this is just a power rule. So you can see that you're going to get n x to the n minus 1. Now what happens if you have like a general function like fx to a nth power? So if you have fx to the nth power using the chain rule, now you can use the chain rule. So you're going to get n fx to the n minus 1. That's the power rule part. And then you have to multiply by the derivative of the inside function. So that's the inside function. You multiply by that. So that's the what we normally call general power rule, or is it power rule plus chain rule? Sometimes we call this a general power rule. General power rule. So it's a general power rule. And then let's look at like two easy examples. So the first one is we're gonna take the derivative of, so let's say d by dx, x to the square root. So this is like a power function. So what we can do, we're gonna rewrite this one as x to the 1/2 power. So that means if you use the power rule, the first version, so you can see this is 1/2 x to the negative 1/2. We do not leave negative index in the final answer. So if you bring it down, square 1/2 means square root power. So you can say it is 2 square root x. So you can write the answer like that. Let's look at another example. How about you have d by dx, x squared plus 1 to the square root. So slightly different. You can see it's a function now. It's not just x here. So x is the identity function, but we have like other functions. So we do the same trick. So it's a d by dx. So we can write this one as x squared plus 1 to the 1/2 power. And then we can use the general power rule here. So it is 1/2 x squared plus 1 to the negative 1/2 times general power rule says you need to multiply by the derivative of the inside function, which is 2x. And you can see 2 and 2 get cancelled and the square root term go down. So finally you can get the answer as x over x squared plus 1 square root. So that is the answer for the second one. So let's look at the third case. So in the third case, fx is a constant but gx not. So in this case, it looks like your y looks like a to gx, something like that. But a is a constant. A is a constant, gx is not. So in this case, what we do, we use the logarithms. So the answer is because we know this result. We know that d by dx e to the x. This is another situation. We know the derivative is ex. But what happened in a general case? So now we have not e, we have something else. So what we need to do, we need to multiply by the natural log of the base. So that means in this case is the answer is d by dx a to the gx is simply a to the gx is going to repeat, no changes, and then multiply by the derivative of the inside function using the chain rule, and also we have this extra term ln a, so you multiply by ln a. So that is the formula we use for the third case. So let's look at again two examples. As the first one, we can look at d by dx 2 to the x. So that means it is 2 to the x times derivative of x is 1, so we don't write it, ln 2. So that is the answer for the first one. As a second one, we can do d by dx 2 to the x squared plus 1. So if you have something like that, what's the result says that actually let's say x cubed plus 1 just to see a slightly different, otherwise you're going to get confused. So let's do that, and then what happens is we can repeat the function. That's why it says repeat the function, no changes, and then times you're going to multiply by the derivative of the inside function. In this case, derivative of inside, which this is 3x squared plus 0 times ln 2. So you can leave it like that, and what we normally do is we try to leave it in a form where you do not get any confusion here. So you can leave it like that. This is a good way, or you can also rearrange the terms and write it like this: 3x squared and then 2 to the x3 plus 1 and then ln 2. So you can write one of those forms, both are okay. There are no confusion here. Yeah, so that's how we do the third one. Let's do the fourth one. So the fourth one is both are not constants. So in this case, both are not constants. So what we can do, so that means your function looks like y equal fx to the gx. And then what we normally do in, like, we can do this problem in two different ways. So the first method is, what we normally do is take natural log of both sides. So we say take ln of both sides. So also what we normally call the log differentiation. That's what we are doing right now, log differentiation. So, and then after we do that, and then we can see that we can, what will happen is you can take ln y, and the other side is going to be ln fx to the gx, and then we're going to use one of those log results. So what the log result says, if there's a power, that's power going to come out. So that's exactly why we do that, then, because you're gonna create a product rather than a power. So you can write this one as gx times natural log fx. So that's what you get. Now this is just a product, so we use the product rule for this one. So that's the idea. It's a product, so we use the product rule. So that's exactly the idea why we take the natural log. So let's take it. So once you take the, so we do differentiate with respect to whatever the variable, both sides. So once you do that, and you can see this side going to be 1 over y times y prime by the chain rule, and then on the other side what will happen is take the derivative of the first term, multiply by the second term, plus derivative, take the derivative of the second term, which is fx times f prime x. That's how you take the derivative of a log function. You write the function in the denominator and then multiply by the derivative on top times this first function, which is gx. So that's what happened. Now you see that's the derivative, and then what you do, you just multiply by y both sides. So that means so in this case y prime is simply whatever y, so in this case fx times fx to the gx, and then we can write the rest here. So this is the answer to the question. So there's another method. So let's look at the second method for this one. So we have, as before, y equal fx to the gx. So what we're going to do, we're going to use one of the pre-calculus result. We know this one. Any x can be written as e to the ln x if x is positive. Or you can write this one, x equal ln e to the x. This is for any x. So any x. So what we can do, we can use the first one for this problem. Actually, we can use this idea for all four. You can see that, you can try it. But here we especially going to use this one for this fourth method. So let's try the idea. So that means what happened. So you can see y equal fx gx. Now if you use e, so it is e to the ln. You repeat the function here, fx to the gx. Now you can see this is exactly same thing as last time. This term going to come in front. So that means you can write this one as e to the gx times ln fx. Now what we do, we take the derivative. If we take the derivative, so you can see it is d by dx, dy over dx, and you can see it's a log function first, it's an exponential function first, so you repeat the function, no change. That's the benefit of having the exponential function, times the derivative of the inside function. That's the product. It's the exact same product that you get from the last time. You can see, you see the similarity here. So same thing, exact same thing. So you take the derivative of the top function, which is g prime x ln fx, plus the derivative of the second function, which is fx over f prime x, and then times gx. And then what will happen now is you replace this one by use the identity again. You can see this is just the fx to the gx. So we just rewrite this one again. That's the idea, because we know that these two are equal. And then we repeat the rest of the function. So this is what you get. And do not remember this as a formula. What you need to do is just when you get a problem, just do it like that. So this is the second method. In the second method, what we did was we used this trigonometric identity, and then after we do that, it's a very simple idea. So we in this case, we don't take natural log of both sides in the second method. You just directly come from, you get the answer, and then you can use the same method for all four. You can try it. And then let's try to do maybe like one example just to see how it's going to work. So as an example, we're going to do this one. So to find the derivative of x to the square root x. We assume that x is positive. So it's an assumption x is positive. So what happened? We're going to use a second method for this problem. So it is the derivative of what we did was we use x equal e to the ln x. So that's the idea. That means if you do that, it is e to the ln x to the square root x. That's the first step. And then it is d by dx e to the square root x times ln x. So the square root term comes in front. And then now we take the derivative using the chain rule. So we take the chain rule here. So it is e to the term ln x times, we can take the derivative of the inside function. So that means take the derivative of the first term, which is 1/2 x to the negative 1/2 times ln x. Then take the derivative of the second term, which is 1 over x times x to the square root. Now what we do, we simplify if we can. Actually in this case we can, and you can see also we can replace this term by the original term. So the first term going to be x square root x, because they are equal to each other. And the second one we can simplify. So you can write this one as ln x divided by 2 square root x. That's the first term. Second term, and you can see square root gonna cancel out, because we know that x equal square root times square root x. So those two, so that means one of them get cancelled out. So you get 1 over square root x. Now what we need to do is just take the common denominator. Common denominator is 2 square root x. So what is missing is 2. So just multiply by 2 the other side. That's how we do with the missing term. You only multiply by the missing term. That's the shortcut. So That means it's going to be if we take the common denominator, it's going to be ln x plus 2 over 2 square root x, and then you can see you can even simplify this one. Square root means half power. Since this is a half power, this is x to the negative x to the 1/2 in this case. But when you bring it to the top, it's going to be negative 1/2. So that means you can finally write this one as x to the you can see the square root x minus 1/2 because the bottom term, and then you can write. Actually, you can write like this, so it's be much better if you write it like that. You can write this one as 1 plus a half ln x. This is much better. So that's the final answer. And you can see we did some algebra also. So you can write it like that. So that's like a second method. How you use the second method to find an answer like that, and see whether you can also get the same answer using the other method, like taking ln. But final answer will be the same. So if you get in an exam, you can actually leave like here. This one is like a good step that you can leave. And but if you can simplify, just simplify, because you like your idea is to write the most simplified form, because then you're gonna get the calculation faster. Okay, so this is how we do it. So let's put everything together now. So this is all the techniques that we learn. So we have y equal fx to the gx. So the first case, both constants. So when both are constants, the derivative is 0. The second one was gx is constant. So you can write the answer like this. So it's the derivative of fx to the n. That's what happened when gx is constant. So it's the n fx to the n minus 1 f prime x. So the third case is fx is a constant. So in this case, we get the we use the normal exponential version. So you have a to the gx, and then you multiply by g prime x, and we have this extra term ln a. Ln a is the base. So now in the fourth case, we have both functions are not constant. So when both functions are not constant, we use the log differentiation. In there are two options. So we use the log differentiation, and there are two ways. So normally, like, how do you know which one we can use? If it's like a small function, like not like a long function, we use the exponential version, as in the example. If it's like a long expression, we use the ln version, because there are so much writing. So that's how you know like which one. So if you are not familiar with any of them, and there are separate video for each of them, and you can find the link in the description, and you can watch them and learn like how to do all those different types. So there are 4 different types, and that's it. Those are the only 4 different types we have for these power functions. Like it's a power function, fx to a gx function. So there are 4 different cases, and these are all 4. Okay, so I hope you learned something interesting, and this will be very useful in your exams and homework and quizzes. So and once you know it, and that's it, because it's not going to change. Okay, so thank you so much for watching.